Right now, inside this wall, tons of liquid stone are trying to burst out sideways. The only thing holding them in is a box of wood, a few steel ties, and the math that sizes them. Leave one tie out, and this is what you get. Everybody films the poor, nobody films the dangerous part. For about a day after that truck pulls away, this isn't a solid wall. It's a flood that hasn't figured out yet that it's trapped. I'm going to prove 3 things. 1, a huge share of what this building costs gets torn off and hauled away next week. 2, the weather you'd call the safe one is the weather that blows a form out. 3, the moment this actually kills people is after the concrete is already hard. Follow the liquid. Start with the lie we all believe, that formwork is just a mold. It isn't. It's a temporary building, and it's carrying 3 loads at once: its own weight, the full weight of the wet concrete, and the crew and equipment standing on top of it. The parts that matter carry stakes, not just names. The ties are the only thing stitching the 2 faces together against that push. The braces are the only thing holding it plumb while it fills. And here's the first surprise. That temporary structure is why concrete costs what it does. Formwork routinely runs from 1/3 to well over half the price of a finished concrete frame. The concrete is the cheap part. The box that shapes it is not, which is exactly why crews fight to use it again. A gang form, a whole wall panel, framed and rigged, gets flown by crane from one lift to the next, built once and reused down the job. A slip form goes further, a ring of formwork that never stops moving, jacking itself up a silo while fresh concrete walks out the bottom edge, already stiff enough to hold its own shape. Reuse is the whole economic game. Now, the reason the mold idea is dangerous. Fresh concrete isn't a solid settling down. It's a liquid, and a heavy one, roughly 150 pounds a cubic foot, heavier than water. A liquid pushes outward, and near the top of a pour, that push climbs with depth. But it doesn't climb forever. As the concrete lower down starts to stiffen, it begins to carry itself and arch against the form. So below a certain depth, the pressure stops growing and levels off. It never reaches the full weight of a solid liquid column, unless you pour fast enough to beat the set. That sideways push, capped or not, is the whole reason ties and bracing exist. It's also why anything light, a hollow void former, a foam block, has to be wired down hard or it floats straight up out of position as the concrete rises around it. And keep that 3rd promise in the back of your mind. The part that actually kills people is still coming. First, you have to see what the liquid is doing. So here's the real question. What decides how hard it pushes? And which weather is quietly working against you? Here's the part almost nobody guesses right. The cold day is the more dangerous one. Cold slows the chemistry, so the mix stays fully liquid longer, keeps stacking pressure at the base, and never gets the chance to stiffen and take itself off the form. Warm concrete sets from the bottom as you pour and quietly relieves the pressure. Same wall, same crew. Pour it cold, and it pushes harder. That's because temperature sits underneath in the formula, and you only need the shape of it, not the algebra. Start from a base number, a floor set by the concrete's weight, and a safety minimum. Add a term that grows with the rate of rise, how fast the concrete climbs the form. Then divide by temperature. Fill slowly, and the bottom sets before the top arrives, so the pressure never reaches full head. Fill fast, or pump from the bottom up, and the whole height goes fluid at once. Full liquid head, plus a real surge allowance, about 1/4 again on top for the pump. Rushing a pour can cost you the form. One bookkeeping note that trips people up. Measure a vertical element, and once it's wider than about 6.5 feet, the code files it as a wall instead of a column. That renaming by itself changes nothing. What actually switches you to the tougher wall equation is a fast rate or a tall pour, not the width. Width picks the category, rate and height pick the equation. Now the tie from the opening. On a form the size of a wall, how much can one missing tie matter? All of it. A single tie left out or set wrong lets the face bulge, and because concrete copies the form exactly, that bulge is permanent. You're grinding it out of solid stone or breaking it out and recasting. Good hardware carries a margin. Form ties and hangers are built to hold about twice their working load. Anchors get a tougher factor, closer to 3-to-1, but not because green concrete is weak. It's because those anchors also carry people and the shock of construction loads. And a failure there isn't a blown form, it's someone falling. Higher stakes, bigger margin. And the human backstop is a form watcher walking the line, eyes on a taut, telltale string. The form doesn't fail all at once, it deflects first, and deflection that keeps growing is the only warning you get before it lets go. Say the form is perfect, you can still ruin the wall in the next 5 minutes. Let the falling stream clip the rebar, the spacers, or the form face on its way down, and the heavy stones ricochet off and separate from the paste. Rock pockets, honeycomb, a weak wall. It isn't the drop height that does it. There's no magic limit on how far concrete can freefall. It's the stream hitting something. So you keep the stream clear, drop it down an elephant trunk or a chute so it lands cohesive, all one material. Then the vibrator, the most misused tool on the site. Its job is to consolidate. Drop it straight down into the concrete, let the trapped air chase up and out, pull it back slowly. Its job is not to shove concrete sideways. Do that and you separate the mix all over again. And the forms themselves get built a little wrong on purpose. A long beam or slab form is given an upward bow, a camber, so that when the load presses down and everything deflects, it settles onto the true flat line instead of sagging below it. How much bow isn't a rule of thumb. It's whatever the engineer computes for that exact span, and a long, heavy one needs far more than a short one. Everything so far has been about holding the form up while it's still liquid. But remember, the moment this thing turns lethal is after all of it, after the concrete is hard. We're almost there. It looks hard. You can knock on it, but is it actually safe to pull the forms? Strength decides that, not the calendar. On one job, the wall forms might come off in 12 hours, and a cantilevered balcony might stay fully shored for the better part of a month. But those are numbers off a specific stripping schedule, signed by the engineer against measured in-place strength. They're examples, not permissions, never off a calendar, never off the last job. And the clock only runs when it's warm. Strength gain really only counts in the hours the concrete stays above roughly 50 degrees. A cold night doesn't slow that clock, it pauses it. Some modern mixes, heavy on fly ash or slag, quietly need close to double the time to reach strip strength, and that surprise has wrecked more than one schedule. So how do you actually know? You test, and you don't trust one test. You crush a cylinder in a press and read the number, but a slim cylinder cures faster than a thick, form-insulated wall, so the cylinder can lie about the real member. That's why crews correlate. A rebound hammer off the surface, a maturity probe logging temperature over time inside the actual concrete. And watch the overpour, because it hides in plain sight. A slab poured to 6.5 inches instead of 6 looks harmless. That's about 8% more concrete and 8% more dead weight on every bay, on every floor. Stack that up a tower, and it's tons of load nobody ever designed for. Which brings us to the part that actually kills people. And it isn't the pour, it's after. It's reshoring. Picture 3 fresh floors. You strip the forms off the top slab, and now it has to hold itself up. Except a young slab can't even carry its own weight yet. So you put reshores back under it, and that new floor quietly leans its load down through them onto the floors below. And the older floors underneath end up carrying the bigger share. It's an invisible stack of load moving through the building, and you cannot see it. 2 ways it goes wrong. Set the reshores tight, jack them up hard, and you lift the young slab, pull its unreinforced top surface into tension, and crack it. So reshores go in snug, never tight, and they have to stack directly over each other, floor to floor. Miss that alignment, and a thin, flat slab gets punched clean through by the post underneath, like a nail through drywall, which is why crews spread the reaction with steel-bearing plates. Get this phase wrong, and a shoring tower buckles, a fresh deck comes down, and it takes the floors below with it. This is the phase that needs an engineer and a plan, not eyeballs. Most so-called accidents were never accidents at all. They were the failures nobody stopped to think through. That's why the person we watch hardest on a site is the rookie. Not because he's careless, but because he's facing the most he's never seen. And there's a cold business fact sitting under the human one. A clean safety record lowers a contractor's insurance rating, and a lower rating lowers the premium on every future bid. Training isn't a cost, It's the cheapest insurance on the job. So, 5 things every pour. 1. It's a structure. Size it, don't guess it. 2. Slower and warmer makes a calmer form. 3. Check every tie and watch for the deflection that warns you. 4. Place it with a clear stream and strip it by strength, not the calendar. 5. Reshore snug, stacked, and engineered. The pour is the part everyone films. The day after is the part that decides whether it stands. Subscribe, and next time we open the collapse case files, the forms that actually failed and exactly why.